In activity 3.5, we're dealing with a family of functions. It looks like h of x equals a times 1 minus e to the negative bx, where both a and b are going to be greater than 0. So, first thing we're going to do is look to see if there's any critical points. We're going to use our first derivative test. So we're going to look at h prime of x. So a is just a constant out front, and then we'll take the derivative of what's in the parentheses. So the derivative of 1 is 0 minus, now we'll do e to the negative bx, which is itself e to the minus bx, and by chain rule, we multiply by the derivative of the inside, which is just negative b. So our derivative, when we simplify this, because we get the 0, everything's just going to get multiplied, and negative times a negative will be positive. It'll be a times b, e to the negative bx. So to see if there's any critical points, we set that equal to 0. ab, e to the negative bx, we set equal to 0. Well, a and b are positive constants. They'll never be 0. And e to the negative bx will also never equal 0. So we actually don't have any critical points. So when we go to make our derivative, we're not going to put any critical points on here. Now our derivative, h prime, well, this is positive, and this is positive. So it's going to be positive everywhere, which means this function is increasing everywhere. So we can say that h is increasing from negative infinity to infinity. So it's always an increasing function. And we'll look at the graph a little bit later in this activity. We're going to do the same thing with the second derivative, h double prime of x. And I'm going to go right from here. A and b are just constants, so they'll be in my derivative. E to the negative bx. We've actually done this derivative before. It's e to the negative bx times a negative b. So simplifying, I'm going to put the negative up front. I've got a b squared term, e to the negative bx. Once again, this is never going to be equal to 0. For no values of x will this thing be equal to 0. So when I make my chart for the second derivative, again, I'm not going to put any critical values on it. The biggest difference now, though, is this is positive, and this is positive, so the whole thing is negative, which means h is concave down everywhere. So concave down on the interval negative infinity to infinity. So our graph is always increasing, and it's always concave down. Part C, we're going to look at the limits. So we're going to look at the limit as x goes to positive infinity of our original function, a times 1 minus e to the minus bx. Remember that b is a positive constant. So as x goes to infinity, this is an exponentially decreasing graph. It's going to go down to 0. So we're going to have 1 minus 0. So this is going to go to a times 1 minus 0, or a. So whatever that a term is. So that a is basically a horizontal asymptote of this graph as x goes to infinity. Limit as x goes to negative infinity of a times 1 minus e to the minus bx. Well, now x is going to negative infinity. A negative times a negative is a positive. So this piece right here is actually going to go to positive infinity. But now we have 1 minus positive infinity, so overall this whole function is going to go towards negative infinity as x approaches negative infinity, regardless of what a is. So we're going to take a look at the graph in the next video and see what that looks like and what changes to a and b do.